Okay, let's unpack this. Have you ever wondered how the tech giants build their incredibly robust and scalable systems?
Hmm.
Or, maybe more practically, how you can translate those high-level system design concepts into the kind of, practical job-ready AWS architectures, the
Yeah.
ones that actually land you that senior role or solutions architect position.
Right.
Today, we're taking a deep dive into exactly that. We're guided by the insights from system design on AWS.
And our mission here isn't just to list off services, is it?
Not at all. It's really to explore the why behind the architectural choices, those tricky trade-offs, and see how leading companies and, yeah, even fast-growing startups design their systems on AWS. We'll go chapter by chapter.
What's really fascinating, I think, is how this deep dive will equip you with not just theory, but the actual practical reasoning, the kind used in real projects.
Yeah.
We'll walk through the key concepts, principles, techniques, try to pull out those essential nuggets. The idea is you'll get a really thorough understanding of how to tackle system design on AWS without hopefully feeling overwhelmed by all the options.
Okay, sounds good. So let's kick things off with the foundational concepts, straight from chapter 1. When we talk about how different parts of a system communicate, we often land on synchronous versus asynchronous.
Mm-hmm.
For a senior engineer, the question isn't just what are they, it's more like when do I choose one over the other, and what are the hidden.
Precisely. Asynchronous, often using message queues, means the sender doesn't block. That gives you way more flexibility, more robustness, perfect for, say, processing big image uploads or batch jobs.
Right.
But it shifts your thinking. You embrace eventual outcomes, not immediate ones. And the debugging challenge, well, the flow isn't linear anymore, is it?
Yeah.
You're tracking messages across queues, maybe multiple services, potential callbacks. It really demands solid logging and tracing to figure out the whole life cycle of an operation. It's a kind of distributed complexity that synchronous systems mostly avoid.
Okay, that makes sense. Now, let's talk consistency guarantees. It's a spectrum, isn't it? And often a source of some real architectural headaches.
Oh, yeah.
On the one end, you've got strong consistency. Everyone sees the exact same data right away. Sounds perfect. But how often is that truly achievable or even necessary in these big distributed systems?
You hit the keyword, necessary. Strong consistency is great in theory, sure, but achieving it across, say, different geographic regions, it often comes at a significant performance cost, especially for writes.
Oh.
Well, imagine every single replica needing to acknowledge a write before the user gets a success message back. That's a cascade of network calls, potentially adding noticeable latency.
Right. And that brings us to the CAP theorem.
Exactly. It becomes less theory and more hard reality. If your network has a communication break between parts of your system, you have to choose.
You can't have it all.
Nope. Do you sacrifice consistency to stay available, meaning maybe some users see slightly stale data for a bit? Or do you prioritize strong consistency, which might mean parts of your system become unavailable until the network heals? You can't guarantee consistency, availability, and partition tolerance all at once during a network partition.
So you have to pick 2 out of 3, essentially.
That fundamental trade-off shapes everything. From which database you choose, like DynamoDB, often leaning towards eventual consistency for high availability, to how you design interactions between microservices.
Got it. So for something like a financial ledger, you'd probably lean towards consistency, right? Except some potential downtime to keep the data absolutely correct. But for maybe a social media feed, eventual consistency and high availability are probably more important. Users can tolerate seeing a slightly delayed post.
Exactly. Understanding that trade-off is just crucial. Speaking of uptime, let's touch on availability itself. It's measured mathematically, right? Total time minus downtime divided by total time.
Yeah, and it's wild how just arranging components differently can impact this. Like if you have 2 components, each 99.9% available, but they're in sequence.
Your total availability actually drops to 99.8% because if either one fails, the whole sequence fails.
But if you put those same components in parallel, how much better can it get? And why do people sometimes overlook this simple idea in early designs?
Put them in parallel, maybe a redundant setup with failover, and suddenly your availability jumps way up, potentially to 99.9999%, because now one can fail and the other keeps going.
Wow.
It's often overlooked because, well, parallel designs add complexity and maybe cost. But for critical systems, the cost of downtime usually dwarfs the investment in redundancy.
And we should distinguish this from reliability, shouldn't we?
Definitely. A reliable system does its job consistently. An available system does its job when needed. You really need both for a useful system.
Okay. So when your system needs to grow, you hit the scaling approaches. Vertical scaling, just adding more CPU or RAM to your existing server, feels like the simplest start. But why does even a well-optimized system eventually hit a wall with this?
Vertical scaling is great early on. It delays the complexity of distributed systems. But yeah, eventually you hit the physical limits of a single machine, or the cost for that next performance bump just becomes crazy expensive.
So then you look at horizontal scaling.
Right. That's your superpower then. Add more standard commodity servers. Distribute the load across a whole fleet. Perfect for handling unpredictable traffic spikes, often more cost-effective at scale.
But there's always a but.
But it introduces significant complexity. Now you're managing distributed state, load balancing, service discovery, ensuring consistent deployments across maybe hundreds of nodes. It's a different world. Many systems start vertical, then make that pivot to horizontal when they hit performance or cost limits.
And as systems grow, maintainability becomes huge,
Yeah.
making it easy to modify or extend things. Got the modifiability, right? Modular design, so changes don't break everything else.
Exactly.
Why is this so often sacrificed when people are racing to launch? And what's the long-term pain?
It's that classic trap, isn't it? Speed over architectural health. Rushing often leads to tightly coupled designs like spaghetti code. The long-term cost. It can be crippling. A small change here breaks something completely unexpected over there. Development slows to a crawl, bugs multiply, developers get frustrated.
Been there.
Yeah. A modular design, thinking about maintainability up front, might seem slower initially,
Right.
but it pays off massively in agility and resilience down the road. You can adapt to new business needs without a total rewrite.
Then there's fault tolerance. The system's ability to recover from failures, hardware, software, whatever, and just keep going. Avoiding single points of failure, using things like replication and checkpointing. You mentioned the fallacies of distributed computing earlier. Can you give an example of how ignoring one of those seemingly obvious truths can really derail a project?
Oh, absolutely. A classic one is the network is reliable. It's so easy to design as if latency is zero, bandwidth is infinite, and packets never get lost.
But reality is messy.
Completely. Networks are unreliable. Packets drop, latency spikes. Ignoring this leads to brittle designs. Think about tightly coupled microservices making synchronous, blocking calls over the network. If the network gets flaky, you get timeouts, cascading failures. The whole thing can grind to a halt.
So you have to design for unreliability.
Exactly. Tools like Netflix's Chaos Monkey actually inject failures on purpose to expose these weaknesses. It forces you to build in resilience retries with back-off, circuit breakers, timeouts.
So it really is this constant balancing act, isn't it? Between cost, scalability, reliability, maintainability, robustness. You're always trading something off.
That's the core art of system design, really. You optimize for user needs within your constraints without sacrificing critical factors. Take network performance, that inverse relationship between latency and throughput.
Right. Higher latency can kill throughput.
Totally, because packets might be waiting for acknowledgments before more can be sent. Understanding this helps you choose, say, TCP for guaranteed delivery when you absolutely need it, versus UDP for speed in things like real-time video, where losing a few packets isn't the end of the world.
Okay, let's switch gears. Let's dig into data storage foundations, chapters 2 and 3. For a senior architect, this isn't just knowing the types. It's about when to use each and the deeper implications.
Indeed. High level, you've got block-based storage, data in fixed-size blocks, quick retrieval, good for databases, transaction logs. Think AWS EVA like a virtual hard drive for your EC2 instance.
And the other main type.
Object-based storage. Unstructured data images, videos, logs stored as objects. Each gets a unique ID, maybe some metadata. Massively scalable. Think AWS S3. The choice often comes down to access patterns and data structure. Do you need a file system? Or highly scalable, addressable blobs of data?
For structured transactional stuff, relational databases are still king, often. Using sequences, adhering to ACD properties, atomicity, consistency, isolation, durability for reliable transactions.
Workhorse.
But when you need to scale relational systems big time, data partitioning or sharding becomes key. What are the main strategies there? What are their hidden costs?
Right. Sharding is essential for scaling relational beyond one node. Hash partitioning uses a hash function to spread data evenly across partitions. Great for avoiding hotspots where one partition gets hammered.
Right.
Range queries become really hard. You might have to query all partitions and piece the results together, the scatter and gather problem.
Okay, what's the alternative?
Range partitioning. You assign continuous key ranges to specific partitions. Makes range queries efficient. But the hidden cost, You have to manage it carefully. If your data isn't evenly distributed across your chosen ranges, you can end up with skewed partitions, creating hotspots again.
And what about database replication? It's not just for backups, is it? How does it affect performance and consistency?
No, it's much more. Replication offers two big wins. Load distribution, you can send read queries to multiple replicas and reduce latency by putting data copies closer to your users.
But the consistency trade-off is key here, right?
Absolutely. Synchronous replication means all replicas are immediately consistent with the leader. Crucial for things like financial systems where every write must be confirmed everywhere, but it adds latency to every single write.
And asynchronous.
Asynchronous replication lets changes propagate over time. Much lower write latency, much better write performance. But you accept temporary inconsistencies between replicas, which brings us right back to that CIP theorem choice.
Okay. But not all data fits nicely into rows and columns. That's where non-relational databases, or NoSQL, come in, focused on scalability, fault tolerance, low latency for huge dynamic data sets. What really pushes you towards NoSQL if you've already tried scaling a relational DB?
Often it's about schema flexibility. Your data structure changes frequently. Or you need extreme horizontal scalability that's hard to achieve with relational. Or your access patterns just don't map well to SQL, like key value stores. Basically a giant hash map. Super scalable, super flexible. Think AWS, DynamoDB, or Redis. They often use distributed hash tables and can have things like leaderless replication or optimistic replication with eventual consistency.
And for more complex data?
You have document stores, like MongoDB or AWS DocumentDB. Store data in flexible JSON-like documents. Great when your data model evolves. They usually scale horizontally with sharding, too.
What about big data analytics?
For massive structured or semi-structured data, especially for analytics, column databases or wide column stores shine. Think Cassandra or HBase. They optimize reads across specific columns, often use eventual consistency. And finally, graph databases like AWS Neptune. They're all about relationships, perfect for social networks, recommendation engines, fraud detection.
So the architectural reasoning isn't just what they do.
No, it's when their specific strengths perfectly match your application's needs, your workload patterns, your growth plans. It's picking the right tool. And often, you might end up using a combination of relational and NoSQL databases in a larger system.
Makes sense. Okay, let's move to caching strategies and implementation, Chapter 4. Caching feels like more than just a performance hack.
Oh, it's fundamental. It's about efficiency, user experience. The main goal is boosting your cache hit ratio, serving data from a fast in-memory store instead of hitting a slower backend database or service.
And when the cache gets full,
Yeah,
we need cache eviction policies.
right. How do you decide what data to kick out to make room? Policies like LRU, least recently used, or LFU, least frequently used, are common. The best choice really depends on how your application accesses data.
But keeping that cache data fresh is critical. Cache invalidation. What are the practical ways to do that, and which one is often the trickiest in a distributed setup?
Several approaches. Write-through invalidation, write to cache and the database simultaneously. Minimizes stale data, but adds write latency. Think e-commerce product prices, you need immediate invalidation.
Okay.
Then there's invalidating on read. Check if the cache data is still valid when it's requested. Guarantees freshness, but adds latency to reads. Simple time to live, TTL, just expires items automatically after a set time.
And the trickiest part.
The biggest challenge, especially with multiple cache nodes, is maintaining cache coherence, making sure all users see a consistent view, even with invalidations happening. That can get complex fast.
Yeah.
Requires careful design.
For deployment, you have in-process caching right inside the application. Super fast. Like for user session data with sticky sessions.
It's exactly. Lowest latency possible.
And then there are content delivery networks, CDNs, like Amazon CloudFront, caching content globally at edge locations. How do CDNs fundamentally change things for a global app?
CDNs are huge. They slash latency by serving content from an edge location near the user, avoids long network trips back to your origin. Plus, they offload traffic from your servers, boosting scalability and resilience, even helping with DDoS protection. It's about making content fast and available everywhere.
When we look at open source caching, Redis is a beast. Why is it often picked over something simpler like Memcached for more complex scenarios?
Well, Memcached is great. Simple, lightweight, very scalable key value cache. Excellent for basic session stores where maybe losing data isn't catastrophic.
But Redis offers more.
Redis goes way beyond simple key value. It has versatile data structures like sorted sets, perfect for leaderboards. It offers pub/sub messaging. It even has persistence options like saving snapshots or logging commands.
So the insight isn't just what they are.
No, it's when does Redis's flexibility justify its added complexity? Or how can memcached still be the better choice for pure, massive scale, simple caching? The critical trade-off is often freshness versus latency. Stricter invalidation means fresher data but more latency. TTL is simple but might serve slightly stale data occasionally.
Okay, next, load balancing and networking fundamentals, chapters 5, 6, and a bit of 9. Load balancers, they do more than just spread traffic, right? How do they boost resilience and security?
Oh, they're indispensable. Beyond just optimizing resource use, they route around failed servers, improving availability. They can offer geographic routing. They act as a reverse proxy, shielding your backend servers from direct internet exposure, which is a big security win. And they can handle session persistence, sticky sessions.
Right, keeping a user tied to the same back-end server using cookies or something. Crucial for stateful apps like shopping carts, although we try to build stateless backends now, don't we?
Ideally, yes. Stateless backends are much easier to manage behind a load balancer, but sticky sessions are still needed sometimes.
And when do you need more than a basic network load balancer? When do you step up to an application load balancer, ALB, working at layer 7? What kind of smarter routing can it do?
An ALB is way more intelligent. Because it understands HTTPS, it can route based on things inside the request, like the URL path, host headers, query parameters, even cookies.
So you could route AB users to one set of servers and AB orders to another.
Exactly. Or route based on user agent for mobile versus desktop experiences. Or implement A/B testing by sending a percentage of traffic to a new version based on a cookie. It enables really sophisticated routing for microservices or complex applications.
To really get networking, we need the basics.
Yeah.
OSI and TCP/IP models. And that fundamental choice, UDP versus TCP, what's a core decision point for a developer there?
It boils down to reliability versus speed. TCP is connection-oriented. It guarantees delivery order, retransmits lost packets, rock solid for critical data file transfers, database stuff. But that handshake and retransmission adds latency. UDP is connectionless. Fire and forget. No order guarantee, no retransmits. Much faster, lower latency. Great for real-time stuff like streaming video or online games where losing an occasional packet is acceptable, but definitely not for data you can't afford to lose.
So the architectural thinking involves things like pushing for stateless backends behind LBs.
Yes, makes scaling and failover much simpler.
And thinking about geographic proximity to reduce latency.
Absolutely crucial. Reducing network hops and round-trip time, RTT, makes a huge difference in perceived performance.
Okay, on to deployment orchestration, chapter 7. A big decision these days, VMs versus containers. For a senior dev, it's not just the tech, it's the operational trade-offs, right?
Totally. VMs give you hardware-level virtualization. Each has its own full OS. That means strong isolation, which is good for security or some compliance needs, but they're heavier, slower to start up.
And containers.
Containers, like Docker, use OS-level virtualization. They share the host OS kernel. Much lighter, way faster startup, more efficient with resources.
So for a new project, when might you still pick a VM over a container, given all the container hype?
Maybe for a legacy app that needs a very specific, older OS environment that's hard to containerize. Or if you need that extreme level of isolation, perhaps for multi-tenant security, where the VM overhead is acceptable. But for most modern cloud-native apps, containers are usually the way to go for agility and efficiency.
And containers are built from container images using Docker files.
Right, those declarative files specifying the layers. Images get stored in container registries for management and distribution.
For managing containers at scale, Kubernetes is kind of the standard now. Basic units are pods running in a Kubernetes cluster. When deploying updates, Canary deployment seems really popular. Why is that so important for reducing risk?
Canary deployment is all about controlled rollout. You release the new version to just a small subset of users first. You watch the metrics like crazy. If anything looks wrong, errors spike, latency increases, you roll back immediately.
Limiting the blast radius.
Exactly. Only that small canary group is affected. If things look good, you gradually increase the traffic percentage until everyone's on the new version. It's a crucial safety net. And then for ongoing operations, monitoring and incident management are vital. Tools like CloudWatch, Prometheus, Grafana, setting up alerts, having automated runbooks, essential.
So the VM versus container choice, deployment strategies like Canary, it's all about balancing isolation, efficiency, and acceptable risk during changes.
Precisely.
All right, let's get into architectural designs and patterns. Chapter 8. These are bigger concepts. Change data capture, CDC for example, sounds simple sync databases, but how does it really change analytics compared to old school batch ETL?
CDC is transformative for analytics. Instead of waiting for nightly batch jobs to load data into your warehouse, CDC captures database changes, inserts, updates, deletes in near real time, and streams them.
So your analytics are always fresh.
Pretty much. You can have real-time dashboards, immediate insights. It turns your data warehouse from a historical snapshot into a living, breathing view of the business. Huge advantage over batch ETL.
Then we have pub sub architecture. Event-driven, asynchronous, decoupled. Sounds great. But how do you choose between a decentralized choreography style, where services just react to events, versus a centralized orchestration style, where something manages the workflow?
That's a really common dilemma in distributed systems. Choreography gives you true loose coupling. Services publish events, others subscribe and react. They don't need to know about each other directly. Great for resilience, simple flows, real-time notifications.
But the downside?
Debugging and understanding the end-to-end flow across many independent services can be really challenging, especially for complex business processes with lots of steps and conditional logic.
Which is where orchestration comes in.
Right. With orchestration, you have a central controller like AWS step functions that defines and manages the workflow explicitly. It calls service A, then based on the result calls service B or C. Makes it easier to monitor progress, handle errors, implement complex logic.
But isn't that central orchestrator a potential bottleneck or a single point of failure?
It can be, if not designed well. You trade off some of the loose coupling for better control and visibility.
So if you were building, say, an e-commerce order processing system, order placed, payment taken, inventory checked, shipping started, which way would you lean?
For something structured like order processing, I'd probably lean towards orchestration initially. The defined steps, the need for reliable completion, handling failures, and compensation logic that structure helps. Choreography might be better for less rigid things, like reacting to user activity feeds or IoT sensor data.
Okay. And microservices. Decomposing systems into small independent services, everyone talks about them. What's the biggest practical hurdle when you actually adopt them?
I'd say managing distributed data consistency and the sheer operational overhead. Each microservice often has its own database, so a business transaction that touches multiple services, that becomes complex. You need patterns like sagas.
Right, managing rollbacks across services.
Exactly, and suddenly you have maybe dozens or hundreds of services to deploy, monitor, scale, and troubleshoot. You absolutely need top-notch CI/CD, centralized logging, distributed tracing, sophisticated observability.
So it's not a free lunch.
Definitely not. You gain immense flexibility, independent scaling, team autonomy, but you trade that for significantly increased complexity in management and ensuring data consistency across the system.
And for routing requests to these microservices, an API gateway often sits at the front. Why is that more than just a simple reverse proxy?
An API gateway is like a reverse proxy on steroids. Yes, it routes requests, but it does so much more. It can aggregate data from multiple backend microservices into a single response for the client. It can handle protocol translation, say external clients use REST, internal services use gRPC.
And handles cross-cutting concerns.
Crucially, yes. Authentication, authorization, rate limiting, caching, request response transformation, logging, monitoring. It centralizes all that common plumbing, simplifying the backend services and the client interactions. Big security and management win.
Okay, this is great. Now let's tie it all together with the real-world system design use cases on AWS from chapters 14 to 18. This is where we see theory hit the road.
Exactly. These chapters provide practical blueprints. Let's start with the URL shortener design, chapter 14. Core problem. Generate short, unique URLs, make lookups super fast. What's a better way than just hashing the long URL?
Hashing can have collisions, right? So the book suggests a key generation service, KGS. It pre-generates unique IDs, maybe in batches, then converts them to a shorter form, like base62.
Smart. Avoids collisions and prediction.
And for storing the mapping short URL to long URL, the book leans towards DynamoDB. How does its schema design help here, especially with partition and sort keys?
It's quite neat. For the main lookup, give me the long URL for this short one. You'd use the short URL as the partition key. That gives you very fast direct access.
What about finding all URLs as specific user shortened?
For that, you'd create a global secondary index, GSI. Use the user ID as the GSI's partition key. Now you can efficiently query for all URLs linked to that user. The key trade-off with GSIs. They're eventually consistent, so a newly shortened URL might take a fraction of a second to show up in that user list query, but it's usually very fast.
And for the initial build, the day zero architecture.
AWS Lambda is a great fit for the application logic. Simple, serverless, no infra to manage, as it scales. Absolutely add a distributed cache like Redis or Elasticache in front of DynamoDB to absorb the read load.
Okay, next, web crawler and search engine design, chapter 15. The scale here is just mind-boggling. Billions of pages, petabytes of data. Beyond just storing all that, what's a core challenge of building the actual search part?
A huge challenge is building and managing the inverted index. That's the heart of search mapping terms, words, to the documents they appear in, along with frequency or position info. It's what makes search fast.
And how do you scale that index?
You have to partition it. Indexing strategies become critical. Do you partition by document? All terms for doc A are on machine X. Or by term? All occurrences of AWS are on machine Y. Each has big implications for query processing, update efficiency, and fault tolerance.
What AWS services fit well here for a day zero architecture?
For orchestrating the complex crawl parse index workflow, AWS Step Functions is a natural fit. For storing the raw web page content and the massive index files, S3 is the obvious choice, durable, scalable object storage. And DynamoDB could work well for storing metadata about crawled pages like last crawl time, checksums, etc.
Moving on to newsfeed design, chapter 16. Super common, super critical for social platforms. For managing the following relationships, graph databases like AWS Neptune get mentioned. What's their specific edge?
Graph databases are built for relationships, finding friends of friends, identifying communities, traversing complex social connections. They do that incredibly efficiently, way better than trying to model it in a relational database with complex joins.
Now, for delivering the actual newsfeed content, there's that big architectural choice. Push model, fan out on write versus pull model, fan out on read. Can you walk us through that when use which?
Sure. The push model is when user A posts, you immediately push that post into the timelines, like inbox lists, of all of user A's followers. Great for users with few followers, timelines are pre-computed, reads are fast.
But for celebrities with millions of followers,
it becomes a nightmare. That's called the write amplification problem. One post triggers potentially millions of writes, very resource intensive, hard to manage.
So the alternative is the pull model.
Right. Fan out on read. When user B requests their feed, the system pulls posts from everyone, user B follows, merges ranks, and returns the timeline. This avoids the massive write amplification.
But doesn't that make read slower?
It can, yes. So you optimize heavily with caching. You'd cache the recent timeline for active users in something fast, like Redis or Elasticache. Maybe the latest 100 posts. Older stuff gets fetched from persistent storage, like S3 or a database, only when needed. Most big platforms use a hybrid approach, mixing push and pull based on user activity or follower count. And definitely multi-region deployment with async replication for availability.
Okay, online game leaderboard design, chapter 17. Real-time ranking, massive user base, instant updates. This just screams in memory store, right?
Absolutely. This is a prime use case for Redis, specifically its sorted sets data structure. You add users to the set with their score, and Redis automatically keeps them ordered by score. Updating a score and getting the top-end players is incredibly fast.
How do you scale Redis itself for potentially millions of players?
You'd likely use Redis cluster. This allows you to shard your data and the sorted set across multiple Redis nodes, distributes the load, memory usage, and processing power. For a day zero build, you might start with a single Redis node, then scale up to Redis high availability HA with replicas, or eventually to a sharded cluster to handle massive scale while maintaining performance and consistency.
Finally, hotel reservation system design, chapter 18. A complex transactional beast. Beyond choosing between, say, Aurora or DynamoDB, how do you tackle critical edge cases like preventing double booking in a distributed system?
Double booking is that classic concurrency problem. You need some kind of distributed lock or atomic operation. A common pattern uses Redis's setNX command, set if not exists. You try to set a key representing the specific room and date range with a short time to live, TTL. If setNX succeeds, you got the lock and can proceed with booking. If it fails, someone else beat you to it.
And if you're using a Redis cluster,
you might need something more robust, like the redlock algorithm, to ensure safety across multiple nodes, though it has its own complexities and debates around it. For the core data storage, both relational, like Amazon Aurora, with its massive storage capacity and performance, and NoSQL, like DynamoDB, are viable. The choice depends heavily on your query patterns and need for schema flexibility.
And for searching properties, especially with complex filters or maybe finding nearby points of interest using location, how do you efficiently pull data together?
GraphQL Federation is a powerful pattern here. It lets your client make a single query, and the gateway intelligently fetches data from multiple backend services. Maybe one for property details, one for ratings, one for pricing, one for availability, and stitches it together into one response.
What about location-based search, like find hotels near this landmark?
For geospatial search, techniques like geohash are common. You encode latitude and longitude into a shorter alphanumeric string. This allows you to efficiently query databases, even standard ones or specialized ones like PostGIS or Elasticsearch's geocapabilities, for items within a specific geographic bounding box. These use cases really show how you combine patterns, services, and careful trade-offs to build real systems.
Wow. Okay, so we've journeyed through the core principles, seen how AWS services provide the tools, and then watched those concepts play out in real-world designs like URL shorteners, news feeds, even hotel booking.
Yeah.
It really feels like a solid blueprint for getting that job-ready understanding.
Indeed. And if you connect it all to the bigger picture, it's clear, isn't it? Becoming a top solutions architect or senior engineer isn't just memorizing AWS service names, it's deeply understanding the why, the trade-offs behind your choices, and crucially, how to adapt your designs as the system inevitably grows and changes. Which kind of raises an important question for you, the listener. When you're faced with your next big system design challenge, how will you identify the single most critical trade-off? The one that will fundamentally shape your entire architecture, and what makes that specific trade-off the non-negotiable one for your particular problem?
That's a great point. The ultimate challenge isn't just picking the right service initially, but that continuous evaluation and adaptation as needs evolve. Thinking about everything we covered, what's the one thing that stands out to you that you want to dig into more after this deep dive?